Hi everyone, hope feeling well. In this video, I will show you how to determine deflection for indeterminate beam with a hinge using Macaulay method. Based on this problem, we need to find the rotation at the hinge, the deflection of the hinge, and the maximum deflection in span BE. Okay, first of all, we draw an elastic curve of the beam. As we can see at point A, there is a fixed support. So there is no deflection at the fixed and there is no slope at the fixed. So it looks like this. Okay, so this is the elastic curve for indeterminate beam with hinge. Then we can calculate reaction at support. Based on the problem given, there is a hinge at point B. That means the beam has two members, AB and BE. The moment equation does not apply to the full beam since there is discontinuity at hinge. That means the moment at member AB cannot transfer to the member BE. So, moment at B is equal to 0. To proceed calculate the reaction, we consider each member separately initially. Okay, I start first with the member BE. Okay, member BE. So, I cut and free body diagram. So, we know that the roller, okay, RD. Okay, I cut at B and 100 kilonewton. Okay, so for each span, okay, 2 meter, 2 meter, and 2 meter. So by using equilibrium equation, summation moment at B is equal to 0. So VB times 6 plus 100 times 2 equal to 0. So we can find VB is equal to 50 kilonewton. Then by using force equation, equilibrium, so VB plus RD is equal to 100. Then RD is equal to 50 kilonewton. Then I proceed with member AB. Okay, so I draw free body diagram. Okay, so I will have, this is a BB, 20, and then 4 meter. Okay, summation moment at A is equal to 0. I have a MA minus 20 times 4 power of 2 divided by 2 plus VB 4 equal to 0. So we know that VB is 50. So I substitute 50 in here. So I will find MA equal to 360 kilonewton meter. Then you can find RA minus VB minus 20 times 4 is equal to 0. So VB is 50. Then RA is equal to 130 kilonewton. Okay, next we find the moment function. Alright, the moment function here, of course, we need to find separately for the member AB and member BE. in this case, we follow the same procedure as integration method. So the first I will do with the member AB. Okay, we cut at the member AB to find moment 1. Okay, so RA is 130 and then moment is 360. So I start from here, x1. Okay, so the moment, summation moment 1 is equal to 0. M1 plus 360 plus 20x power of 2 divided by 2 minus 130x equal to 0. So M1 is equal to 130x minus 10x power of 2 minus 360. Okay, the next one for member BE. Okay, so the member BE, cut off section. Okay, we need to find M2. Okay, this is a VB, which is a 50. Okay, and then you have a 10 or 100. Okay, then cos we have 50 at the D. So we start here is x2. So this is 2 meter, 2 meter. Okay, summation moment 2 equal to 0. M2 minus 50x minus 100 x minus 2, okay, minus 50 x minus 4 equal to 0. So the moment function for 2 is equal to 50x minus plus 100 x minus 2 plus 50 x minus 4. Okay, next we find the slope and deflection equation. So I start with the M1. Okay, 130x minus 10x2 minus 360. So integrate to find the slope. 130 x power of 2 minus power of 3 x power 3 minus 360 x, okay, plus c1. Then integrate again by 6 power 3 minus 10 12 power 4 minus 360 divided by 2 x power of 2 c1x plus c2. Okay, as usual, this is equation 1 and this is equation number 2. So now we proceed with M2. So EI okay, so So equal to, okay, right, so differentiate, okay, so 50 x power of 2 divided by 2 plus 100 x minus 2 power of 2 divided by 2 plus 50 divided by 2 x minus 4 power of 2 plus C3. Okay, then we integrate again. 50 divided by 6 x power of 3 plus 50 divided by 3 x to 3 plus 25 divided by 3 4 plus C3 x plus C4. So this equation is equation number 3. Then this one equation number 4. Okay, next we need to solve the unknown C1, C2, C3 and C4. So we take a look back the beam problem. Okay, at point A is a fixed support. So at a fixed support, we know that there is no deflection, V0, and there is no slope, okay, 0. So when x equal to 0. Now at roller support, okay, for member BE, when x equal to 4 meter and V equal to 0. So this is the 3 boundary condition. Okay, we can calculate to find the unknown C1, C2, C3 and C4. In the case of member BE, more typical analysis to calculate the constant of C3 and C4. Okay, so we must first determine the deflection at B. Okay, what does it mean? Let's we take a look from the figure again. Okay, at B, okay, here there will be deflection. Okay, so the deflection at B here for member AB. So deflection B for member AB is equal to deflection B for member BE. So this is called continuity equation. Deflection at B, member AB, when x equal to 4 equal to deflection at B for member BE when x equal to 0. Okay, so now we have one more equation for boundary condition. We can apply this case, okay, this boundary condition for equation number 2 and equation number 4. Okay, now we can solve the unknown for member BE. Let's start with deflection at B for member AB when x equal to 4 equal to deflection at B for member BE when x equal to 0. Okay, we substitute into equation number 2 and equation number 4. So 130 divided by 6 times x power of 3 minus 360 by 2 x power of 2 minus 20 divided by 24 x power of 4 equal to 50 divided by 6 x power of 3 minus 50 divided by 6 x minus 4 power of 3 minus 100 divided by 6 x minus 2 power of 3 C3 plus C3x plus C4. So I substitute. So in this case we have a 4, 4, 4. Now this is 0, this is 0, this is 0, this is 0. So in this case x minus 4. 0 minus 4 is negative 4. So we need to eliminate based on Macaulay method is equal to 0. Okay, and also here is negative 2. We eliminate is equal to 0. Therefore, we can find that C4 is equal to negative 1707. Now, we can use another boundary condition for member BE, x equal to 4, V, okay, equal deflection equal to 4V or delta is equal to 0. So substitute into the equation number 4. Okay, 56. Okay, 50 divided by 6 minus x minus 4. 100 divided by 6 x minus 2 power of 3 plus C3x plus C4. So I substitute, this is a 0, x is 4. Okay, C4 we already find from the previous, we substitute here. And now we can find that C3 is equal to 327. Okay. Now we already solved all the unknown C1, C2, C3 and C4. Then we need to rewrite again all the equation for slope and deflection. So we start with this member of AB. Okay, 3x squared 130 divided by 2x power of 2 minus 360x minus 20 divided by 6 x power of 3 plus C1. C1 is 0. So V equal to 130 divided by 6 power of 3 divided by 2 minus 20 divided by 24. Okay, plus C1 is 0, plus C2 is 0. Then for member BE. Okay, dx squared is equal to 50 divided by 2 x power of 2 minus 50 plus divided by 2 x minus 4 power of 2 minus 100 divided by 2 minus 2 divided by 2 plus, okay, C3 is 327. Then for deflection, 6 power 3 6 okay, then for deflection, okay, then for deflection, divided by 6 6, 3 minus 100 divided by 6. Okay, plus with 327 x. Okay, minus with C4 is 1707. Now, we can answer the following question. The first question is to define the rotation at the hinge. In this question, you need to find for both member AB and member BE. So, let's recall the elastic curve of the beam. Okay, we need to find rotation for member AB and rotation for member BE. Okay, we start with member AB. Okay, we find the rotation at B when x equal to 4 meter. So we substitute into the equation. Okay, dv over dx is equal to 130 divided by 2 at power of 2 minus 360 x minus 20 divided by 6 x power of 3. So we substitute x equal to 4. Okay, so we can define dv over dx or theta b is equal to negative 630 over EI kilonewton meter square. So, okay, the angle is like this. Okay, next, we find rotation for member BE. Okay, member BE, rotation at B when x equal to 0. So substitute into the equation. Okay, 50 divided by 2 x power of 2 plus power of 2 x minus 4 power of 2 minus 100 divided by 2 x minus 2 power of 2 plus 3 to 7. Here we substitute x equal to 0, 0, 0. So 0 minus 4, negative 4 cancel. 0 minus 2, negative 2 is cancel. So therefore we can find dv over dx equal to theta b equal to 327 over EI kilonewton meter square. So is here theta b. Okay, now we want to define the deflection of the hinge. In this case, you can use either member AB equation or member BE equation to define the deflection of the hinge. Okay, so I choose to use from member AB equation. Okay, the deflection at B. Deflection at B for member AB when x equal to 4 meter. Right, I will substitute into the equation for member AB. 6x power of 3 minus 360 divided by 2 x power of 2 minus 20 divided by 24 x power of 3. Okay, so I substitute 4 into the x. Therefore, I can find V is equal to delta B is equal to negative 1707 over EI kilonewton meter cube. So it's going down. Okay, the last question is to define the maximum deflection in span BE. Right. In this case, there is two possibilities based on the elastic curve. So based on the elastic curve, we can know either deflection at B or deflection at E. So you already defined the deflection at B. Now we go for define the deflection at E. So deflection at E for member BE. Okay, the deflection at member BE. The maximum. Right, so you already know the deflection at B, negative 1770 EI. So now we need to find deflection at E when X equal to 6. So in this case, we use the equation from member BE. So EI B equal to 50 divided by 6 x power of 3 plus 50 divided by 6 x minus 4 power of 3 minus 100 divided by 6 x minus 4 power of 3 plus 327x minus 1707. So I substitute x equal to 6, x6, so x6, here is x6. So we can define that V equal to delta E is equal to 1055 divided by EI, kilonewton meter cube. So it's going up. So when you compare between these two, you compare, right? Therefore, deflection at B is maximum. Maximum deflection is equal to delta B equal to negative 1707 EI kilonewton meter cube. Right? So negative is just sign is going down. Okay, that's all for now. Thank you for watching.